Welcome to this session on process synchronization. Till now, we'll try to see that what we have learned till now. So we find that we have seen that types of a computing system, that is systems which are batch system or PCs, distributed systems, etc. Then we'd seen what is OS, and we said that OS can be defined as a resource manager. And then we had introduced the concept of a process, and we said that process is an instance of executing a program. And we had also seen that how the process is managed inside the machine. And then we had tried to see one of the very important aspect, that is managing the CPU. That is, we looked for a process scheduling algorithm, and the various scheduling algorithm we had seen with a view that these algorithms, some of the algorithms would try to maximize CPU utilization, some of them would minimize response time, increase throughput, and offer fairness to processes, etc. We'll try to see that what is the issue which is there with the process synchronization. We'll try to understand. So in this session, what we are essentially going to discuss is that how do we maximize the CPU utilization. And we find that the simplest approach to maximize the CPU utilization or improve the efficiency, the approach could be either carry out a multi-programming or carry out what we call as a multi-processing. So we find that in a uniprocessor systems, processes are interleaved in time, and whereas in case of a multiprocessor systems, processes are overlapped in time. We'll see that what do we mean by interleaving and overlapping of a processes. We find we would also see that interleaving and overlapping of the processes, they would improve the overall processing efficiency. But if one more thing is to be seen, or we will observe that if interleaving and overlapping of processes is not carried out in a controlled way, then the result produced by these processes could be unpredictable. And then what so we find that there is a issue in terms of carrying out the interleaving or overlapping, and we will in this session, what we'll try to do is we'll try to figure out a way or a mechanism to solve some of those issues which are encountered. So a simple concept, let us look at a interleaving concept of a interleaving. So in this case, we say that we have three processes, and interleaving is a mechanism where processes are interleaved in time. So we say that in this case, what we are indicating that the processor P1 starts in the beginning and executes up to a certain point of a time, and at this point of a time, perhaps the process P1 maybe it goes for a IO service, it makes a IO request, so it gets blocked, and when it gets blocked, probably the P2 starts at the same. Here we have shown exactly starting at a same instance of a time, whereas in practical scenario, what would happen that there would be a small time which will be consumed by the dispatcher process. Dispatcher would take a finite amount of a time, whereas in this example we have assumed dispatcher doesn't takes any time. So you find that P2 would execute, and then we are saying that P1 once again would execute, and then P3 arrives, executes for some time, and so on so forth. So we can see that starting from this time to this time, we find that processes P2 and P3 have also executed. So let us assume that if P1 had to go for an IO, so if suppose the processes were not interleaved, then in that case what would have happened, that P1 going for a IO, the time in which it is carrying out a IO would have got completely wasted. So this time would have been completely wasted, this time would have been completely wasted. So we find that the time by which P1 completes execution, probably P2 and P3 have also completed their execution. So from this diagram we can very clearly see that interleaving would allow us to improve the efficiency of, or improve the throughput of a machine. Let us look at a concept of overlapping. This concept is applicable for the case where you have multiple processes. So since we have multiple processes, processes can start simultaneously in parallel. So the diagram indicates that, so we are assuming here that we have three processors. We have three processors and three processes. So we assuming here that the P1 comes first and it starts executing, and then process P2 comes and it starts executing on the another processor, and then process P3 at some point of a time comes and it starts executing. So we find that if at this juncture of a time, at this point of a time, if we try to look, we find that P1, P2, P3, all the three processes are executing. So in case of a multi-processing system, we would find that simultaneously multiple processors would be executing. So the execution of a processes are overlapping. So that is how this is what the concept of overlapping is, and we can again see very clearly, because of overlapped execution, the efficiency of execution would improve. We shall be able to execute more number of processes per unit time. We need to understand that why we have said a while ago that when we carry out interleaving and overlapping of the processes, there are certain issues which are going to arise. So we need to understand why these issues are going to arise. There are a few very apparent reasons. One, that the system has a finite resources. And when multiple processes are trying to access those resources, there can be a contention, and that can be an issue. Then some kind of ordering for resource allocation, etc., is to be carried out. Then we also know that when the processes are executing, we cannot make any assumption in terms of relative execution speed of the various processes. How fast, how slow a process would execute at a different point of a time is going to be, it cannot be predicted, and this is primarily for the reason that when the same process executes at a different point of a time, it is possible that at a different point of a time the resources which are available in the system are going to be different. So they can be relative speed of execution of processes will not be possible to predict. And then we also know that sometimes it is required that processes they share the resources. So when the resources when we are talking about, we can say that resources can be of two different categories. One can be a shareable resource and other can be a non-shareable resource. The example of a shareable resource is a kind of a read-only file which can be shared across many users simultaneously, whereas example of a non-shareable resource would be a printer, where at any given point of a time only one process could be printing, it cannot be shared with the multiple processes. So we would have resources which are going to be shareable or non-shareable, and the issue mainly arises when we have a non-shareable resources which are required to be shared among the processes. So these are the few issues which we find that this is which one would need to resolve. And whenever the sharing is going to be carried out, this would mean that some kind of a coordination among the processes is required to be carried out. And in general, we find that one of the most commonly used approach for process coordination or process communication, inter-process communication, is by means of a shared memory. So sharing is again required, and then the other important means is inter-process communication. We will study about them in our later sessions. Let us look at an example, a very simple examples, and then with the help of this example itself, I'll be able to show you that if the processes are not controlled properly, then the result can be actually pretty unpredictable. So we saying that let's say that we have a procedure, we calling it a procedure echo, which has two variables. I'm saying in and out, and I am saying that this procedure echo is the one which procedure echo takes input from the keyboard and displays it on the screen. This is a common thing where whenever you type in a key, whenever you press a key, the pressed key gets displayed onto the screen. So let's say that this is a function representing the task of taking the input from the keyboard and displaying it onto the screen. So here the example so we find that we define two variables, out and in of type character, and then we have a function input which takes this input function is using a in as a variable and a keyboard as a device. It takes a two parameter, that which device to use for taking the input. So when input is invoked, it tries to read the information from the keyboard and it stores the information into a variable named in, and then out variable is assigned the value of in, and then output function is used for outputting it onto the display device. So this is a simple function which does the job of reading a keyboard and displaying it. And let us see that two processes are trying to invoke the same function at inside a system. So what happens? So let us see that this is an example. So I am saying that same example I am trying to show. So I am saying that a process P1 is trying to execute, and then followed by a process P2. So in this case, if suppose process P1 executes the instruction input, and after this this process gets suspended. So when process P1 would execute, so let's say that when input statement gets executed, let's assume that the user would input a value x. So at this point of a time, the variable in will have a value x in this. Now process P2, coming to a process P2, and process P2 we let's say that after execution of a P1, process P2 starts and it executes a input statement, and let's say that here the value which is entered is y. So this executes, after that this executes, so out will become equal to y, and then you will say output, you will invoke the output function which will display output on a screen y. Now let us assume that after executing this instruction, the command returns back to the process 1, that is the process 1 once again gets its chance to finish the execution. So we can very clearly see that these two processes are sharing the in and out variable, and after return from here, the value of in is y, whereas in case of a process in input time, when this statement was executed, the value of in was x, which has been modified in this case. So now when this program executes, the output value will become equal to in, that will be equal to y, and output which is going to be displayed is going to be y. So both the processes, I am assuming that user 1 was executing process P1 and user 2 was executing process P2. So you would find that one of the user P2 would get the correct result, that is he pressed y and he got a display of a y, whereas P1 actually pressed x and got a display display of y. So we can very clearly see that if the processes are going to be interleaved and they are not controlled properly, then they can be unpredictable results. So when the operating system, so in this case we can very clearly see that the result is dependent on the order in which the execution is taking place. For an example, if process P1 had executed all the 3 instructions and followed by a process P2, then there would have been no ambiguity. So this is a one problem. So we find that a result of a process when it comes to the operating system, what we need to do is the result of a processes must be independent of the speed of execution of the other processes. So this is one of the requirement of the operating system. Let us also understand that how the processes interact with each other. A system can have a large number of processes, and let us see that how the processes are going to interact with each other. So in the system we find that the processes can be categorized in different category. The one category, that set of processes which are unaware of the existence of other processes. So if we assume that there is a place where in this case what is happening, that it is assumed the one process is not aware of the existence of the other process. So as a consequence, this process tends to believe that all the resources are going to be available to it, and it will try to access. And as a consequence, when such a thing would happen, it will lead to a competition for the resources, because simultaneously multiple processes would want to access the same resource, and since they are not aware of existence of the other processes, probably there would be no cooperation, and these processes would compete for the resources. And we will see that we know it very well that whenever the competition is going to be there, there is somebody who would win and there is somebody who would lose. And it is also possible that, let's say that 2 processes which are trying to access a resource and they are competing for the same resource, and it is possible that one of the process would never be able to access the resource, because in competition it always fails. So as a consequence, this particular process may completely starve for the resource. So one of the problem which is faced when the competing process is there is what we call as a starvation, the process of problem of a starvation. Another category of processes, that is processes are indirectly aware of existence of other processes. This is a classic case where we know that when the operating system uses a shared buffer for reading the keyboard input and other things. So processes are aware that whenever I/O is going to be carried out, there would be other processes which would probably share the resource, but processes in this case do not know the name of the process which is going to access those resources. They know that somebody would access, but they are not directly aware that who is going to be accessing. Nevertheless, even in such case, because the processes are indirectly aware, they at times would show kind of a cooperation. So it will ease out a certain issues. It will help us. And then the last case is that there are processes which are directly aware of the existence of each other. So it is something like that. There are two friends, and they know that, and let's say that they have a one book. So then one book to share. Then what happens that they can actually cooperate. They can decide that one friend can decide that, okay, he is going to read the book in the morning, and other friend can decide that he is going to read the book in the evening. So there can be a cooperation, and the contention can actually be avoided. So this is broadly, we would say that processes can be in a different. These are the three different categories in which the processes can be there. And we have seen that when processes compete for resources, the problem may occur, problem of a deadlock may occur, problem of a mutual exclusion and starvation may occur. Shortly we will try to see that what is the meaning of a deadlock, or let us just try to understand that what the deadlock is. So let us take an example that the two friends are there, and there is only one pen, and there is only one paper, and they are attending a class and taking notes. So now what happened that these friends, they come in, one of them picks up the pen and other picks up the paper. So now the person who has picked up the pen waits for the other person to give the paper, and the person who has picked up the paper waits for the other person to give the pen. And we find that both of them, since these two people are holding resources, they are waiting for other to release the resource, and nobody is releasing the resource. So you find that they get into a kind of a scenario which is a deadlock. They are not able to carry out the task. None of them are able to take the notes. So this is what the deadlock is. We will study about the deadlocks in a greater detail in coming sessions. Then an example of a mutual exclusion. So if we look at a printer is a non-shareable resource, and if two processes need to access, then the processes must access the printer in a mutually exclusive manner, meaning to say process 1 takes the printer, completes its printing job, and once its job is over, then only the process 2 takes, or vice versa. So mutual exclusion is important, and we had already seen that why the starvation can occur, and so we know that when processes would compete, the problem of a deadlock, mutual exclusion and starvation would occur. And we also know that when processes would cooperate, probably some of the problem can be avoided, but deadlock and starvation still might occur. So essentially we find that there are three issues when we talk about a concurrency and a issue. So we find there are three important aspects which one needs to handle. One is a mutual exclusion, another is a issue of a starvation, the third is a deadlock. So we find that cooperating and competing processes can cause problem when they are executed concurrently. We need a kind of a solution. We need some kind of a solution which will eliminate these problems. So let us briefly look at that how the cooperation is achieved. The cooperation among the processes can be achieved primarily by two means. One we call as a shared memory. So it is something like there is a memory area which can be shared among all the processes. So one process, any process which wishes to communicate with the other process, it can go into that memory area, write the message, and the other processes can read it from the shared area. But we can very clearly see that the message, while the one process is writing the message, other process should not be able to modify it. So what is required is that when a process is writing, the process should access this memory in a mutually exclusive manner. So in mutual exclusion, we find that when process for the process cooperation, if we are sharing the memory, then mutual exclusion is one of the important requirement. And the other could be that what we call as a message passing. Message passing is an approach where the processes are directly aware of the existence of the other processes. They know the process, which are the processes, so that direct messages can be sent. Of course, there are mechanisms where message passing can be also carried out with the help of unknown, when we are not directly knowing which are all the processes which are there, but we will see that how that is done. So we find that for a solution to the concurrency issue, if we wish to use the concurrency in a successful manner, then there are few things which are required. The one, we need to be able to define what we call as a critical section, and critical section we can consider as a something like a non-shareable resource in an abstract way, and then enforcement of a mutual exclusion. So these are the two primary requirement for successful use of a concurrency control. And any solution which is proposed must guarantee the mutual exclusion, and the solution also must guarantee what we call as a progress, meaning to say that when there is no process which is trying to access the resource, and if there is another process that makes a request for that resource which is not being accessed or not being accessed by any other, then the requesting process should immediately be granted the resource. There should not be any delay. That is what we mean by saying that progress. And then the other thing is the processes requesting these resources should not be delayed indefinitely in the sense that they should not get into, the solution should not lead to what we call as a deadlock, or solution should not lead to what we call as a starvation. And as earlier also mentioned, that any solution which is being proposed should not make any assumption in terms of relative execution speed of the processes. And the last one is but the very important thing, that the process would remain inside the critical section for a finite amount of a time. What essentially it means, that processes would hold the resource for a finite amount of a time. They would not monopolize the resource. So the process design should be such that it would request the resource. Once granted the resource, it will use it, and then once the usage is over, it will faithfully release the resource for others to use. So these are the few requirements which any proposed solution for process synchronization would need to satisfy. So let us see that what are the various approaches which are possible for. We will initially try to handle. We'll handle one by one. We'll try to handle mutual exclusion in coming session, and then we'll devote few separately few sessions discussing about that issues and handling the deadlocks. So when we try to look at that, what are the various approaches by which mutual exclusion can be achieved, we can broadly put the solution in a three category. The one we call as a software approach. So the software approach is a one where I would say that a user is responsible for enforcing the mutual exclusion. The user would write the code which will ensure that mutual exclusion among the processes would be achieved. So that is the one approach. The other approach we would see that what are the pitfalls in such an approach. Then the other approach is was hardware support, that if some kind of a hardware support which can be provided for the purpose of achieving the mutual exclusion. So there are in that also we would discuss about two approaches, that is one disabling of interrupts, and then the other approach is based on a provisioning of a certain special instructions supported by the processors. We will see that, and then finally then we will also try to see that some kind of a support coming from the operating system. So we find that operating system also would provide some kind of a support, and we will try to study two of the things, that is one is a semaphore and another is a monitor. So we will see that how the mutual exclusion can be achieved using all the three approaches. So let us look at a first approach, software solution. So let's say that here I have given a small code. So I am saying that I have and this approach I am calling it as a solution 1, and we'll develop several solutions for this. So where here we have a turn variable which can take a value of 0 or 1. Let us say that we have a process 0 and a process 1. So process 0, whenever any of the process comes, any one of the process wants to access the critical section, what it does, it comes and checks that if the turn is, it checks the turn variable. So we can say that there is a blackboard on which the turn is initialized. So in the beginning, let us say that a turn is initialized to 0 or a turn is initialized to 1. So let us say that a process 0 comes, it will check that if the turn is equal to not equal to 0. Turn is not equal to 0 essentially means what? That turn is equal to 1, because here we have said that the turn can take a value between 0 and 0 or 1. So if turn is not equal to 0, then turn is equal to 1. What does it mean? It means that it is a turn of process 1 to get into the critical section. So as a consequence, this algorithm, if we see what happened, that we can very clearly see that when this statement will execute while turn is not equal to 0, do nothing, meaning to say if the value of turn is equal to 1, the process 0 would execute set of instructions which will be not doing anything. It will just be executing do nothing. It will go inside a loop which will do nothing. But if the turn is equal to 0, then in that case what happened, that it will come in and then execute the critical section. So when this condition is false, when this condition becomes false, that is when turn will become equals to 0, then what happened? Then the process 0 would execute, and after executing the process 0, see the process 0 is showing a good behavior in the sense that after executing the critical section, now it wants to give a chance to the next process. So it goes and marks the turn equals to 1, and in same way, same analysis I can say that the process 1 also does, and it will mark the turn equals to 0. So let us say that this is a one solution. So let us say that we are trying to implement a software solution, and in this case we are only assuming that there are only two processes. The whole solution will become very complex if we have a large number of processes. Let us try to see that what is the drawback of this particular process. So we can see one thing, that this solution guarantees the mutual exclusion. For an example, we can see that. So let us say that a process 0 comes and it finds that the turn is initialized to 0, let's assume that in the beginning turn is initialized to 0. Process 1 comes and wants to execute. It will check if turn is equal to 1. It will find turn is not equal to 1. So, it will wait. Now, so while let us assume that while the process 1 is waiting, then process 0 comes, it checks and it finds okay, it is its own turn. So, it goes and executes, and after executing the critical section, it marks the turn equals to 1. As soon as it marks the turn equals to 1, the process 1 would now be able to execute. So, we find that the critical section, when one process is executing, the other process is not able to get inside the critical section. So, the mutual exclusion is guaranteed, that is, the critical resource is executed in a mutually exclusive manner. But we can see the example from the previous example, we can see the drawback, one of the drawback, that is pace of execution of one process is determined by the pace of execution of other process. For an example, if in the beginning the turn variable is initialized to 0 and process 1 wants to come and execute, and let us say that process 0 never wants to execute the critical section, then process 1 will not be able to get the chance. So in this case we find that there is a problem. The pace of execution of one process gets determined by execution of the other process, and we can very clearly see that in this case a strict alternation would occur, that is, the process 0 would execute, then process 1, then process 0, then process 1, and so on. So that is a one problem, and we can also very clearly see that if suppose that the process executing fails inside the critical section before changing the turn, then so if process 0 was executing, it failed inside the critical section, and so it was not able to mark the turn equals to 1. As a consequence, we find that process 1 would never be able to access the critical section. So these are the two major drawbacks. We can very clearly see that the solution at a first look would first look would look good, but then analyzing a bit deeper, we find that these solutions are not meeting our requirement, or they are meeting only one of the requirement, that is mutual exclusion, but there are other problems they can have. So why, the question is that why this solution has not worked. So we find that in this case what is happening, that we directly, the process 1 uses the name of our other process for entering into the critical section. It is not checking at a state of the other process. So this is one major issue. It checks that whether the turn is equal to 1 or whether the turn is equal to 0. That is, it is checking that whose turn it is. It is not checking what is the state of a process. So we will try to, so our next solution which I am going to propose is going to be doing something where a state of a process is going to be checked rather than directly checking the turn, and we will see that how that solution works out. So in this case what we are doing is we are saying that we are defining to maintain the state of the process. I am saying that we are defining a flag which is an array of 2 element, and these can be initialized to true or a false in the beginning, right. So in the beginning I say that both the it is initialized to in the beginning this is initialized to false. So let us see that how the now the modified approach would look like. So what we do here is the process 0 comes, checks the flag of the other. If the flag of the other is false, then it means that the other process, so process 0 comes, it checks the flag of a process 1. So if the process 1 is the flag for the process 1, that is, the flag of 1 is false, that essentially means that the process 1 is not interested in doing the critical section. So So what can happen, that it can actually it can get inside. So in this case what happened, that the process, it finds that the flag is false. So we are saying that while flag 1, we are saying that do no op. This essentially means that if the flag value is true, then don't do any operations, meaning to say the flag, that process 1 is already executing. So here we are trying to see that what is the status of a flag. So the process 0, when it comes, it checks the status of a process 1. It tries to find out that if the process 1 is trying to execute, if it is executing, it tries not to do anything. If process 1 is not executing, then it comes and makes its own flag equals to true, and then proceeds for a critical section. And after doing the critical section, once it returns out, it makes its own flag false. So let us see that how the execution would happen. So let us assume that in the beginning both the flags are false. So what happens, that you would check if process, while flag of 1, you would find flag of 1 is false. That means that you will not execute NOP, you will come and execute this. So the process 0 will mark its own flag equals to true, which was false initially. It will go to the critical section, and it will, after doing the critical section, it will mark its flag equals to false and finish it off. In same way the process 1 would execute. So this is a simple solution. Let us look at that. Are there any pitfalls in it? Let us analyze that whether it satisfies all the criteria which we had laid down, that is a mutual exclusion and other things. So here we are trying to show interleaved execution. So I say that let us see that in the beginning the process P1 came, instead of calling this process as a P1, I would call it as a 0, and this process I will call as a 1. So let us say that a process P0 came, and it started checking. So it checks the flag of a process 1, and since in the beginning both the flags are marked as a false, so process P0 finds that the flag of 1 is false. But so it finds that a flag is false, meaning to say it need not execute this part, it should go and execute this. But before the process P0 could execute the flag 0 equals to true, what happened? It was, let us say its time slice got expired, and control was transferred to the process P1. So now process P1 came and checked. So process P1 now so we should see very clearly that P0 has actually not been able to modify its flag. It is still false. So when P1 comes and checks that while flag 0 is false. So we find that it also finds the flag. So process P1 also finds that a flag 0 is false. Now after executing this, let us say that once again the time slice for this process P1 expires and a control returns. So when control returns to the P0, obviously because the process P0 has found the flag 1 equals to false, so it goes and marks its own flag equals to true. And after this, if once again the interleaving operation is performed, so it may happen, you can see that a flag 1 also will marked as a true, and after that both the processes can access the critical section. So we find that this particular solution even does not guarantees the mutual exclusion. This is worse than the previous solution. So let us so these are a few observations for this proposed solution. The one is that that we have already analyzed that it does not satisfy the mutual exclusion, and we know that if these processes are individually accessed in a ordered manner, then it will give me a correct solution. So actually in this case what is happening, that the solution correctness is dependent on the relative execution speed of process execution. So that is another reason, and worst case we find that this particular process doesn't satisfy the mutual exclusion. So the question arises that why this, we had in a previous case we said that since we were directly using the name instead of checking the process state, that's the reason we failed. And then in second approach we found that we were using the state, but still the approach using this approach we still got failed. Primarily the reason is that what happened, that once a process observes the state of other process, after that the state can change. That is the problem. If suppose somehow we can ensure that once one process has seen the state of other process, and after that the state cannot be changed, then the problem can be solved. The major problem is the second approach is a failure because of this reason. So this particular problem can be sorted out in a very simple way. That what is done, that so as soon as the process 0 comes in, what we are saying, that the very first thing it will do is it will mark its flag equals to true. That is, when process is going to start, is going to go and is wanting to access some resource, in the beginning itself it is sort of indicating that it will mark its flag equals to true, and then it checks the status of a flag of a other process. So in this case, so now if suppose this instruction has executed, and after that another process comes and it tries to execute the instruction, same instruction. So what would happen? Both the processes would actually end up marking their own instructions equals to true. So there is going to be a small problem. We'll analyze that. Let us first look at a solution, the way solution is going to work. So I am saying that as soon as you come, you say that you have an intention of going and doing the critical section, and then you check whether if the other person is having an intent or is already doing. If other person is doing, then you do not try to access the critical section. If the other person is not trying to access, then you come and access the critical section, and after accessing the critical section, mark your flag equals to false. That is, you would indicate that you are finished. So this is a simple thing, simple solution. The one thing very clearly seen, that this particular approach would guarantee me the mutual exclusion, because the process states would not change after one process has actually one process has seen the state, then it is not going to change, because we can see very clearly that the state change instruction is placed before the checking instruction, checking of the flag instruction. So the state cannot change, therefore we would say that a mutual exclusion will be guaranteed. But let us assume that we have I wanted you to see a simple scenario here. That let's say that process P0, the statement number 1 executes, that is a flag 0 equals to true. Then process 1 comes, it also marks its own flag equals to true. Then process 2 comes. So now after execution of an instruction, this instruction, first instruction by both the processes, now when process 0 tries to execute while flag equals to 1, it finds that flag equals to 1 is true, and when process 1 tries to do, process 1 also finds the flag equals to true. So you find that both the people have marked their flags equals to true, and now both of them are not able to proceed. So they sort of they get into a kind of a complete deadlock. They will not be able to move. So this is a problem which we would need to resolve. So we find that this approach satisfies the mutual exclusion, but we have seen that this approach would lead to a deadlock. We need to analyze that why this approach failed. So we find that a process sets its state without knowing the state of the other, and that's the reason that deadlock occurs, because each process can exist on its right to enter the critical section. And we furthermore we can very clearly see that these processes, once they have marked their status as a true, there is a no backing off mechanism. That is, they find that okay, there is a other process who has also marked true, and they are waiting for one of them to become false. So there is a no backing off mechanism. You find both are insisting that they would want to go through. They would want to access the critical section. I call such kind of in a actual metaphorical sense, I call these processes as a discourteous process. So let us solve this particular problem. So in this approach, the fourth approach which we are presenting here, what we are going to do is we are going to provide a backing off mechanism, and so let us see that how the approach is. So we start with the same thing. We say that a flag equals to 0, and we will say that while flag equals to 1. So what we are doing, that if flag 1 equals to true, then what we are doing, we are trying to back off. We are saying that this particular process 0 will go and mark its own flag equals to false, wait for a random amount of a time, and then mark its own flag equals to true. So the assumption here is that when it would mark its own flag equals to false, then during the period of time, if other process is trying to complete its execution, it will complete, or if other process is trying to execute, it will execute that. So there is a backing off mechanism. After marking its intent, that is, it wants to do a critical section. If the flag 0 marked it's true, but as soon as it found that flag 1 equals to true, what it did, it went and marked its flag equals to false. So this is a approach. This approach looks sound, looks good, because in a previous example we had seen that why the third solution failed was primarily for one reason, that there was no way of backing off. So once the backing off scenario is created, we find that it may just work well. But let me just show you a case under which this can again fail. For an example, let's say that in the beginning the process P0 marks its flag equals to true, then process P1 comes, also marks its flag equals to true, then let's say this while statement gets executed. So what it does, that when the while statement gets executed, so it checks that, let us assume that it checks that the flag is, while the flag is equal to 1, flag 1 is equal to this condition is checked. So we are checking that if the flag 1 equals to true. So we find that okay, the flag 1 is equal to true. So now what happens, that let's assume that after this check the command transfers back to the second process, and second process also checks that if the flag is equal to, flag 0 equals to true. So second process also finds flag 0 is equal to true. Now what happens, that first process also proceeds to modify its flag to false, and a second process also proceeds to modify its false, and both of them, they wait for equal amount of a time and once again come and modify their flag equals to true. So as a consequence, now what happened, that you can see that even though with the help of a what we calling is as a backing off mechanism, these two processes, they are not able to move. Probably with a little difference in execution speed, the solution would work fine. I just to appreciate this, I would just want to tell you one, just want to remind you of one story, which is a story regarding the Lucknow Nawabs. And there is a story that these two of the Lucknow Nawab, they wanted to board the train. They reached to the platform, and they would say "Pehle aap." So the one of the Nawab told to the other one that please board the train, and the other Nawab told the other person that please board the train, and both of them kept insisting that you go first. Meaning to say, these two Nawabs were becoming quite courteous. They were very courteous. Lucknow is known for its courteous Nawabs. So if you remember, in a previous case I said discourteous process. So now in this new approach, we thought that we can introduce the courtesy in the process. So we've gone from one extreme to the another extreme, that in a previous case the processes were discourteous, and now these processes are showing too much of a courtesy. As a consequence also, they are not proceeding further. So something else is to be done. So we can very clearly see that these are the approaches. These are the approaches we have gone to various solution, starting from solution 1 to starting from approach 1 to fourth approach, and we find that still we have a issue. Finally, I just show you a final solution, which is a correct solution. So I leave it for you to analyze that why this particular solution is a correct solution. This is pretty obvious from why this would be correct. The basic fact, which see, I've been trying to show you various approaches. I had given you a solution in 5 steps, and the fifth approach happens to be the most correct approach. Why I did it? I wanted you to appreciate that when a user is trying to write a solution for a mutual exclusion, it is going to be a very tough task, and any small oversight can lead to an incorrect solution. So this is we've seen that the solution, how difficult it is to write a correct solution with the two processes. The complexity would increase when the number of processes in the system are going to be very large. So I at the end, I would only want to make one comment that the software approach for implementing the implementing a mutual exclusion is not a great idea for several reasons. That it puts a lot of burden on a programmer, and it has a scope of still it has a tremendous scope of errors. So we will try to, in a next session, what we'll do is we'll try to see few more approaches which are more practical and which are probably at times used. Some of them are definitely used in the systems for achieving the process synchronization. Thank you very much.